What I'd like to talk about today is the automated generation of SPARQL. My first time I saw SPARQL, I thought it was too complicated, and so I did what a lazy person would do, was to try and figure out how to generate SPARQL for me. And I'll be looking at two really complicated examples, and then I'll put them aside and do some really simple ones. Does this?
No, I think you should just use
arrows. Okay, sorry. I think the base problem is that rule-based applications for the built environment have made very little progress since the Singapore E-Plan check system in around the year 2000. They're not trusted because there's a gap or a large number of steps between the source text and the programming that implements them, and there's a lack of explanation of results or options being suggested. They're also uneconomic to develop and maintain because you need to have subject matter experts. In the case of code compliance, the inspectors, you need application programmers and you need experts from the target domain in the room to develop the rules. And they've all turned out to be very limited, bound to a specific scope, a particular target format, a particular workflow, and they haven't really been able to be generalized in any way. So starting in about 2007, I started to think about, was there a better way? And I came up with a methodology called RAISE. RAISE stands for Requirement, Application, Selection and Exceptions, and you'll see there's a logo there to remind you. And normally, well, its most common application has been to normative requirements, building regulations, client requirements, with the aim of automated compliance checking. But you can also apply it to definitive registers like dictionaries, lookup tables, classification tables, and so on. And in fact, you can also apply it to think about descriptive or narrative reports like BIM and GIS, which are virtual reports of how you think the world is or should be, or will be, and so on. So we're going to focus on normative requirements to start with. Here are two examples. On the left, you can see a regular clause from a UK-approved document that's mandatory guidance, Part M for accessibility. And you can see that the text has been coloured in one of the four colours. You can see probably most clearly that there is some green applicabilities at the top. There are some clauses, actual requirements boxed in blue, and you can see that within those requirements there are certainly some exceptions. The other thing I want to pick out is the table below. We can also mark up tables so that when we come to do automatic colouring, the colouring is enough for the computer to understand the regulation. On the right-hand side is a clause from the UK construction regulations. And we can mark that up as well, but until the previous speaker finishes his work, there's no target database that we can check. So the only time that this text is ever used is if there's a court case, and so on. As soon as we have a construction digital twin, then this will be able to tell you if you're executing your excavations in a safe manner. And you can see that there's a very large exception in that document because the clause starts, no construction work shall be carried out. And then there's a big unless, and then there are things that you have to do to make your excavation safe. So even taking an individual clause, they are quite substantial and complicated, but the markup is enough to make it machine readable. So, and let's do a simpler example now. Top left. External doors and windows shall be at least 1200 millimeters wide unless featuring a lock. I don't know why you would have such a rule, but it's a nice example. And you can see below it, I've done the markup, that the applicability of this rule is to external things. There's a selection of objects, doors and windows. There's a requirement at least 1200 millimeters wide, and there's an exception featuring a lock. So just doing that colouring, we can generate the other three documents on the screen. Bottom left, you can see a concept graph, which shows that the markup has created a tree on its side, which goes from a general predicate and points to various logical tests on the right, metrics or facets, and they are joined together by logical operators. And that's generated completely automatically once you've done the markup. You can do the opposite thing on the bottom right side, where we can generate a visual program. It starts with the inputs on the left and goes through two kinds of widget to end up with the result on the right. Again, generated completely automatically. The top right example is the original text, but with write-in boxes added in systematically. And so I can actually answer the questions. So I can think of a particular object in my BIM or anywhere else. It could be a telephone call, a discussion with someone, and we can answer the questions. And as soon as it's decided whether this is a pass or a fail, the word pass will appear at the top. Things that aren't relevant will disappear. So the markup is the start of a lot of very useful tools to support the idea of automatic code compliance. We also have an engine which will consume it directly and check a document like that against an IFC file systematically. But one of the things we can do is, let me just go back a moment. One of the things we can do is say, can we convert the knowledge that exists in either the very complex examples or this fairly simple example, can we convert that into ordinary rule languages like SPARQL? And before we can answer that question, we have to talk about trees and mice. There's a tree, and you can see that it starts at A, and you could wander up and down this tree, a little mouse could wander up and down this tree, visiting every node, and when it gets to a leaf node, there is a question to be answered. And then we will eventually come back down again. So this is an ordinary tree iteration algorithm, nothing very special, depth first tree iteration. The reason that we're interested in trees is that Rays creates or converts written text into being a tree ontology. There are lots of boxes which become objectives, which are effectively branches in the knowledge tree, and those branches can contain metrics, which are testable, leaves, and they can contain other branches. And that's a pretty good definition of a tree. So our mouse, in running around this tree, is making decisions. Each decision is a particular event, like I'm going to start, I'm going to go up to the next branch, I'm going to a neighbouring branch or leaf, I'm going to come down towards the trunk again, and then I'm going to finish. So that's how we make sure we check every piece of knowledge in a tree. Now, we want to be able to convert that statement into SPARQL. And on the right you can see the complete statement with prefixes at the top. The really interesting part is highlighted in blue. And you can see that the word window in the example has been converted by going through another table, which is a dictionary that says in English the word windows is equivalent to shackle or SPARQL, doesn't matter which, IFC window. And so in iterating over the tree, we can substitute the marked up word with the equivalent expression that we want in our SPARQL statement. You'll also see that the word "and" has been converted into a double line, which means "or," and so on. And how that happens is slightly more interesting. So if we, to do that, we have to consult another dictionary, which is a little bit more complex. In fact, it's a table, and it looks like this. You can't read it. Okay, well, down the middle, you've got events, and I've highlighted an event which our mouse might consider before a subsequent selection. Okay, so, and looking up from this table, it gets the double bar symbol for "or." And by listing all the events, we can actually generate the SPARQL query. And it works. And there you can see that an even simpler case, doors should be wider than 800 millimeters. And using Rasmussen's viewer, LDBIM, it's picked out the doors that don't comply. We can generate test cases either automatically. Everything is either true or false. And so with 2 metrics, we get 4 test cases. Everything works fine. That's absolutely super. What happens if we think about if those answers could be true, false, or unknown? Then it gets a lot more serious, because we end up with 9 test cases, 5 more, and depending on where the unknown appears, we can actually get the wrong outcomes. It's great if we're testing the width of the door, it's unknown, it's okay, it gives a plausible answer. But if its applicabilities are unknown, then we will get the wrong answer. And this is my big anxiety about the closed world assumption, that things that are not known to be true are taken as being false. And that can lead to really dangerous outcomes. My next line of inquiry is to say, perhaps SPARQL and SHACL isn't the right answer. Let's look at the web ontology language, which is apparently open world assumption, and see if we can infer whether objects in our BIM model are in one of 3 classes. In this case, is it a member of a class called door width rule false, or door width rule unknown, or door width rule true? And so we might be able to still do compliance checking by adding class assignments to the objects in a BIM model. Thank you.